Thank you. So I'd like to tell you about a new way of constructing Hamiltonian operators in loop quantum gravity, which we have developed in Warsaw together with Emanuele Alessi, Mehdi Assaniussi, and Jurek Lewandowski. So the plan for the talk is here. Since we didn't get the general talk about loop quantum gravity earlier today, I will start with a very short introduction to the theory. Then I'll tell how we construct this new version of the Hamiltonian and what advantage it has over the earlier constructions. And then I'll finish with some concluding remarks. So a classical starting point for loop quantum gravity is general relativity written in the Aztecar variables. So the Aztecar connection A and the densitized triad E. The constraints of the theory are the Gauss constraint. The Gauss constraint, the diffeomorphism constraint, which encodes the invariance of the theory under internal gauge transformations and under spatial diffeomorphisms. And then the Hamiltonian constraint, in some sense, contains information about the dynamics in the theory. In the quantum theory, the basic operators are not the connection and triad themselves, but they are suitably smeared version of the variables. So we have the holonomies of the connection along curves in space, and then the conjugate operator is the flux of the triad over surface. And the Hilbert space is spanned by so-called spin network states. The spin network state is labeled by a graph, and each link of the graph has a holonomy in some representation of SU2. And then the nodes of the graph there are intertwiners or invariant tensors of SU2, which make the state gauge invariant. After you impose diffeomorphism invariance as well, you identify all graphs that are related by diffeomorphism. So then the gamma here is really not labeling a single graph, but an equivalence class of graphs under diffeomorphisms. So at this point you have imposed all the constraints except the Hamiltonian constraint. And this problem of dynamics can actually attack it from several points of view. The first and somehow most obvious one is that you try to impose the Hamiltonian constraint as an operator equation in the quantum theory. So you construct the constraint as an operator, and then you try to find the space of solutions to the constraint, and then the information about dynamics is somehow contained in the scalar product of the states in this physical space. So instead of this, there's another option, which is that instead of considering gravity by itself, you consider gravity coupled to some kind of matter. And then the role of this matter field is to provide a sort of a relational time variable with respect to which you describe the evolution of the gravitational field. In this approach, the dynamics of the quantum theory is described by the standard Schrödinger equation where this Hamiltonian is an expression which is somehow related to this Hamiltonian constraint. And then in addition to this, there's also the so-called covariant approach, where you sort of forget about the Hamiltonian constraint altogether and instead you try to define the dynamics in terms of a path integral which you construct by using sort of suitably discretized version of the basic holonomy and flux variables. So this covariant approach was already a subject of some previous talks, but it's somehow completely outside the scope of this talk. And this concludes a very short introductory part, and now I will move on to the main part of the talk. And so I describe how we can construct either the Hamiltonian constraint operator in the first approach or the physical Hamiltonian operator in the second approach. And this construction, which I will show you, it's especially designed for this second approach, because the construction enables us to make a symmetric Hamiltonian operator, which you obviously should have if the role of this operator is to be the generator of physical time evolution. So the starting point for the construction is the identity which I'm showing here. So the first line is how the Hamiltonian constraint is usually written in the Astekar variables. But you can show that this expression is equal to the expression on the second line. And it's this second form of the constraint that we take as a starting point for the construction of the operator. And in this usual form of the constraint, the two terms are, the first is called the Euclidean part and the second the Lorentzian part. And I'll keep using this terminology, even though we should remember that this object which I will be calling the Lorentzian part is not actually the same object as the object on the first line, which is what people usually call the Lorentzian part of the constraint. So the advantage of starting with the expression that I showed on the previous slide is that the Lorentzian part of the constraint becomes somehow simple in the quantum theory. So this kind of expression can be quantized by using Rege's formula for this action integral. Rege's formula is giving this integral in terms of the lengths and angles in some kind of decomposition of the space manifold into tetrahedra or even other kind of cellular blocks. And these lengths and angles are well-defined operators in the quantum theory. We can just take these operators and then we get this Lorentzian operator as an operator which it acts on a spin network state. It acts by changing the intertwiner at each node, but it doesn't modify the graph on which the spin network is based. So in the Euclidean part of the constraint we have the curvature of the Astekar connection. And to quantize this we can write the connection in terms of a holonomy around a small loop. And because of this, the operator that we get, it acts by going to the nodes of a spin network and attaching a loop to each pair of edges at the node. And it turns out at this point, if you want to be able to construct a symmetric operator, you have to be a little careful about how you define this loop. So the traditional way of assigning the loop, which was invented by Thiemann, is shown here. So you place the loop so that part of the loop is overlapping with the existing edges of the spin network, and then there's one additional part. And then in these overlapping parts you couple the spins using the normal rules for coupling spins, and this produces terms where the spins have been raised or lowered by 1/2. So in particular, if you start with an edge is carrying spin 1/2 to begin with, then in the resulting state you will get a term where the segment of the edge has spin 0, so this means that this part of the edge just gets erased. And this causes a problem because when the edge is erased, you lose information about how the edge was tangent, possibly to any other edges which are at the node. So we can sort of define a notion of order of tangentiality basically by taking two edges which are tangent and comparing the Taylor expansion of the tangent vectors around the node, and then seeing at which order we first see the expansions being different. So here we see that if we have, to begin with, we have the edge being tangent at two different orders, but in both cases the spin 0 part of the resulting state is exactly the same. And this causes a problem for what would be the adjoint of this operator, because the supposed adjoint operator, it is acting on this state here. It, so to say, doesn't know how it's supposed to put back the edge. And so when it's acting on this state, we get all these terms where the edge is tangent to some other edge at all possible orders, and then we get this infinite combination of terms which, well, is a state of infinite norm, and this means that this adjoint is not a good operator in the space of spin network states. Now, since our goal, or at least one of our goals, is to define the physical Hamiltonian in the case where we describe the dynamics by evolution with respect to some kind of relational time. And this is not good, because we need to be able to have a symmetric and eventually self-adjoint Hamiltonian operator. So we have to somehow improve the prescription for the loop, and we do it in this way, which is shown here. So we add the loop so that it's tangent to the pair of edges to which it's added on, but it doesn't overlap any of the existing edges in the graph. And in the case that we are adding the loop to some edge which already is tangent to some other edges at the node. We look at all the orders of tangentiality between all the existing pairs of edges, and then the loop is added at one order higher. And it results from this construction that the adjoint of the operator is a well-defined operator on any spin network state. And because the loop which is added by the Hamiltonian as a kind of unique order of tangentiality, then it's always clear which is the loop that the adjoint operator is supposed to remove, and then it just never happens that the adjoint would produce an infinite result acting on any state. And this is much better because now we can construct a symmetric Hamiltonian as some kind of a symmetric combination of this new Euclidean operator and this adjoint. So the conclusion is that we actually make some concrete model. The case which we have done is we take a free massless scalar field as the matter field, which is used as the internal time variable. Then we get a model of loop quantum gravity, which is on the mathematical level completely nice and well defined, and there is no problem. The dynamics is described by a symmetric Hamiltonian, and we can even construct it in such a way that it is self-adjoint. So the thing that is left to do at this point, which is certainly not a small thing at all, is to understand how we can test the physics contained in the model by making some kind of concrete calculations with the model and to see if the results are physically reasonable or not. And to do this, it is clear that we need to come up with some kind of suitable approximations by which we can somehow understand the dynamics of the model in some way that we can carry out in practice. And this is all I want to say, and thank you for the attention.
Thank you. Questions?
So this essentially you can map some diagrams that you can calculate with this C operator into other simplex, right? Or
sorry, I didn't hear.
I have seen your diagrams that you can map with this C operator. You can map from a diagram to another one, right? Is it right or not? I have seen in your figure. I'm not an expert, so I'm just asking. Do you understand the question?
I'm not sure.
Okay, if you return back, so it seems that what happened? You are mapping with C this diagram to.
Yeah, so there is some kind of a schematic picture of how the operator is acting on a spin network state. Okay. So this picture is showing what happens to the graph on which a state is based, and there's also the intertwiner at the node where something happens as well, but it is not shown in the picture at all.
Okay, and so this technique can simplify calculation or not?
Mm,
No.
It is not clear at this point. So the point of this we are at somehow a less advanced stage, because we have like for the first time that I am aware of, we have like completed the definition of the model in some concrete and mathematically acceptable way, and the question of how to calculate with the model is something to be done in the future.
Okay, one more question. With this old proposal, people were concerned about this ultra locality, so you just add these loops, and if you keep acting on it, there's just loop after loop added at a vertex, and they don't seem to propagate to nearby vertices. That was for a constraint. Now it's for a Hamiltonian, which may be easier to picture what happens in terms of evolution. So are you worried about the same kind of ultra locality, or is there some way to get around?
Well, there's some free, I mean, because you can essentially symmetrize the operator in many different ways. So basically you can at least take C plus C dagger, or the square root of C times C dagger. In this C plus C dagger case, the action of the operator is as local as the old operator. And in the case of C times C dagger, square root is something different, because instead you have a state which has one loop somewhere. Then first you act with C dagger and you remove the loop. Then C acts and adds the loop at every node of the graph. I mean, you get a sum of terms like this. Yes, it is true. So
except that you don't have actually the self-adjointness. And that's problematic for the evolution operator.
Yeah, that's true for the evolution, but not for the...
For the constant, it is even advised to not to. And even the product actually will not give you the non-locality that you will obtain here.
Okay, thank you again, and thanks to all speakers this afternoon.